In the last part of this lesson, we focus on the concept of heat. In this first video, we discussed the seemingly peculiar case of processes which take place isothermally and involve the exchange of heat between system and surroundings. First, let us consider the case of an ideal gas isothermal expansion. We said earlier that the heat is involved when there are differences of temperature. So how can there be heat involved in an isothermal process? In this example, we have a gas exhibiting a volume V under a pressure P at a temperature T equal to that of the surroundings. The gas container is diathermic, so the system is in thermal equilibrium with the surroundings. We now allow the gas to expand in this environment until it reaches a pressure P' and exhibits a volume V'. The temperature of the gas remains constant, isothermal process, because of the diathermic boundary and the fact that the temperature of the surroundings is constant. Let us try to find the signs of the work, the change in energy and the heat for this gas as a result of this isothermal expansion process. The gas expands under some finite external pressure, so the gas is doing work on the surroundings, and W is negative. Let us now consider the change in energy of the gas. Energy has two components for any substance: the intermolecular potential energy associated with the interactions between its molecules, and the kinetic energy associated with the motion of molecules. Since we are dealing here with an ideal gas, such intermolecular interactions are assumed to be negligible. So the only non-zero component of the energy is the kinetic energy. The average kinetic energy of molecules in an ideal gas depends only on the temperature. Since the expansion is isothermal, the kinetic energy of the gas molecules, therefore, the total internal energy remains constant. We say U equals a constant. We therefore conclude that delta U, or the change in energy, is equal to 0. We now anticipate the first law of thermodynamics to be discussed in our next lecture, and write delta U is equal to Q plus W, from which we conclude that Q is equal to minus W. So the heat involved in the isothermal expansion of an ideal gas is positive. In other words, heat is flowing from the surroundings into the system. In the case of an ideal gas, the flow of thermal energy from the surroundings into the system is exactly balanced by the flow of mechanical energy from the system into the surroundings, so the energy of the system remains constant. In your homework, you will need to think of whether this would hold true for a non-ideal gas or for a liquid. You will need to think about the conditions under which the energy of a system depends only on temperature and not on the system's volume. A second example of isothermal processes involving heat is the case of chemical reactions. Indeed, chemical reactions can be run in a reactor placed in a very large bath kept at constant temperature. Again, here we are assuming that our system, a reactive mixture of urea and oxygen gas, is contained in a reactor with diathermal walls and a freely moving piston. The reaction at room temperature between urea and oxygen is a combustion reaction. Full oxidation of carbon atoms to gaseous carbon dioxide and hydrogen atoms to liquid water molecules. Under such conditions, nitrogen atoms are unreactive and end up forming molecular nitrogen gas, or N2. Combustion reactions are always exothermic. That is, they release heat, or we say Q is negative. Looking at the reaction equation, you conclude that the number of moles of gas consumed by the reaction, in the present case 1.5, is smaller than the number of moles of gas formed by the reaction, here 2. Hence, the reaction leads to an increase in the number of moles of gas. The temperature of the system remains constant since the system is in thermal equilibrium with the constant temperature surroundings, thanks to the diathermal reactor walls. The concurrent increase in the number of moles of gas and the invariance of the system temperature would lead to either an increase in volume if the piston was free to move, or an increase in pressure if the piston position was locked in. The freely moving piston in this problem ensures that the reactor volume can change in proportion to the number of gas molecules. Hence, the increase in the system volume results in work being done by the system on the surroundings. That is, W is negative. Because there is less energy stored in the chemical bonds of products than in these of reactants, the change in energy associated with this reaction is negative. The conditions under which this reaction is carried out, freely moving piston and diathermal walls, lead to work and heat being transferred from the system into the surroundings.